Right, are we ready?
Yes. So I should thank everybody for coming, and please come and sit on the chairs a bit front, further forward. I think everybody's here.
Hey, mate, can you make it go?
Yeah. Oh, I'll go again. Voice operated now.
I'll give you a hand signal if you like.
I'll just press place.
Okay.
And yeah, again, there's beer in the fridge. And we're going to have some pizza afterwards. When it gets here, probably about 7.
Okay. Right. This talk takes about an hour and a quarter. I tested it the other day. The first half is about why functional programming, and it's less technical. And then I go into how functional reactive programming works. And then at the end, I've got about 15 minutes of code, so you can fall asleep at that point if you like. Right, that's me. I'm a bit thin on the biography there, but I'm the author of Sodium Reactive Library, so that's my bias there. And if you want the code and everything, it's all there, all the examples in here. So I've got 4 slides on what. Well, first of all, I call it reactive programming. It's traditionally called functional reactive programming. So I'm treating reactive programming as more of a marketing name because I think it's time to market it to the mainstream. So it's a composable or modular way to code event-driven logic. It is also a different way of thinking because you're not conceptually pushing, you're conceptually pulling your events. It's an observer pattern that doesn't suck, and it can actually be a drop-in replacement for the observer pattern. I'll get onto the observer pattern in a moment. It can also be a technique to help rescue commercial projects that have hit the complexity wall, and by that I mean that the time to add a feature or fix a bug has got out of control, and I'll talk about that a little more as well. So these are the sort of applications that it's really good for. It only really applies to event-driven stuff, so there are certain problems where it isn't useful. But there's also some interesting potential with ideas people have had of things that you can use it for, like database applications and those kinds of things. Okay, so you are probably all familiar with the observer pattern. The idea is that you register a listener on some object, and when you've finished, you remove the listener, and the listener is an object that you hold as the client of that, on which you get called back when some event happens. So it's good because it inverts the dependencies in the program, which is what you want, and it allows it to be extensible. Without the observer pattern, your code would not be extensible. So separates concerns, that's a major thing. So it gives you a loose coupling, and it's better than polling. It's much more efficient than polling. So it's simple, effective, and widely used. What could possibly go wrong? Well, these things. So I've made a list of some of the things that can go wrong with the observer pattern. And what they all give you is compounding complexity. And that means that your program is not scalable, and I will explain that a little more as well. So the first thing that can go wrong is you can have unpredictable order of processing. So let's say C is listening to A, C is listening to B, and B is listening to A, and when B receives an event, it also propagates one which C picks up. So what order do these arrive at? It depends on what order the listeners were registered in, and that's not generally what you want. So the second thing that can go wrong is missed first event. So I'm illustrating here that when the consumer first gets registered with the source, it has to get the current value of whatever it is monitoring from that source, just because the source might have sent events before, and when you register you might have missed the first one, and that's a very common problem. Okay, messy state. This is probably the biggest problem. So what you ideally want is you want your logic to have some kind of flow of control. That's what people normally would like, but basically using callbacks, especially if you've got multiple sources of information, it completely messes up that anything that might resemble a flow of control, and you end up with these really ugly state machines. There are typically a lot of undefined states as well, the way they're generally done. So it means that if you make a coding mistake, you can get your state machine into illegal states. It's very, very difficult to debug and that kind of stuff. So I've given this illustration of dragging some object around using a mouse. This is not complete by any means, but it gives you the idea that you've sort of got this mutating state as you go, and there's no real flow of control. Okay, so threading issues. Observer pattern can be quite bad for things like race conditions and those kinds of things. If it happens to be running on another thread and you remove a listener, how can you be sure you're not going to get called back? These are the kinds of questions that come up. Typically in industry you use one thread, so your standard design for a GUI library, for example, has one event thread, which is really silly. Basically, event-driven code is naturally parallel, so why do we throw it away? That's the question. Right, leaking listeners is pretty simple. If you forget to deregister a listener, usually in the standard implementation of the observer pattern, then you get a memory leak. You get something that's not doing anything, that's still getting notified. So what happened to the safety that garbage collection was supposed to give us? Okay, accidental recursion. This one I have had in a real program, and so I am speaking from experience here. The idea is that process state is a kind of update. Whenever a new event comes in, you just go to process state to bring everything up to date. So what it can do is it can notify the listeners that it's ready for something, whatever that thing might be. Then the listener might go off and do something. But if that listener generates an event that causes this to get called back, then that is going to happen afterwards. And that can get very confusing very quickly. So that's another problem with the observer pattern. Right, so it's got ill-defined semantics. That leads to compounding complexity, which makes the behavior really hard to predict, and you end up with angry customers. So, reactive programming has the property of compositionality. Now, some of you might not like this definition. This is the best one I could come up with. It seems to be quite hard to pin this one down, but essentially I'm doing it in terms of complexity. The idea is if you have two software components and you put them together, they don't have subtle interactions that make the complexity compound. It's a simple addition of two simple concepts, and they don't have strange interactions. So that's the idea behind compositionality. So what all this means is that if you've got compounding complexity, then it means that it increases exponentially with size, and people don't know it's happening. So the program gets bigger and bigger, and then you hit the scalability wall after a year or two. So reactive programming can help you break through that, and I propose it's a really good idea to do that. So, but you've got to remember it's only for event-based code that this applies to. So it doesn't solve all problems, it just solves this particular problem. But it does tend to be where a lot of the worst bugs are. Right, so I'm saying it can be used as a drop-in replacement for Observer because it's hard to stuff up what you're doing. It's very carefully checks things. You're really writing something that looks a lot like pure logic, so the clarity of intent should be there. And it is composable, as I've mentioned, but importantly it's not all or nothing. You can introduce it in stages, and that's why it works very well for existing commercial projects. So, you might be wondering why not just start with the observer pattern and deal with the issues as they arise. Well, I think basically what I found is that what I think is going on is a lot of people have invented reactive programming independently, and they did it by dealing with the problems of the observer pattern. So it turns out implementing a reactive library is actually quite hard. Sodium, which is my implementation of it, is only 900 lines of code, and it's pretty much the most difficult 900 lines of code I've ever written. So I think that's because the problem itself, the problem of dealing with events, is fundamentally hard. So I think the observer pattern is basically hire purchase, and with reactive programming you're paying it all up front. So it's quite painful for the person who implemented the reactive library, and then there's a learning curve for the person who uses it. You know, that is what you'll run into if you just try and fix the observer pattern. Right, so in theory, compositionality means that the complexity versus size graph of your program, complexity versus program size, it would be closer to linear, which is a very good thing. Anecdotally, we kept waiting for the wheels to fall off, but they never did. So this is my brother, Anthony Jones. We've got Jay Shepherd is coming later, and he's been on the same project, so you can ask him about that. Do you need a functional language to use reactive programming? No, you don't, but static typing is a good idea. So I've implemented Sodium in Haskell, Java, C++, and I would like to implement it in C# and Rust, and anything else I can think of when I find the time. So there is surprising similarity between independent reactive library implementations, and lots of people have invented it without realizing that that's what it was called. And there's a guy called Heinrich Apfelmus, and he did a reactive library called Reactive Banana, and he compared the primitives in Sodium against Reactive Banana and found that they were identical apart from the names. So I think that's a very good sign. I think we're actually boiling it down to something fundamental. We may not be completely there, but I think we're heading that direction. Right, so what I want to achieve with this talk is I want to show the problems with Observer. I want to claim that reactive programming fixes them all. I want to explain why I think it fixes them, but I'm not attempting to prove it to you because I think that's a little bit difficult to do in a talk. So you will need to actually try it. So I thought I would mention actor as well, which is the model that's used in the Erlang programming language. It actually is intended to solve a lot of the same problems, and I've just drawn up a little comparison chart. They all give you this separation of concerns, which is the whole point of these kinds of things. Actor solves most of the problems, and I think it's these first two that it doesn't really solve. Now, importantly, actor doesn't have that property of compositionality, so it's I don't know, I'm not really experienced in it, so I don't know how it compares in terms of practice, but and the point here is reactive programming gives you the strong consistency guarantee. So consistency means that if you modify some state somewhere in the system, that it's observable everywhere in the system. And that doesn't really work so well with distributed processing. So it's not really, there is potential for reactive programming to be used in distributed programming, but it hasn't really been reached, and whereas Erlang is proven and works in distributed programming. Okay, I'm just going to give you a little bit of a rundown on performance and parallelism. Essentially, I talked about how with Observer we often throw the parallelism away because we try to restrict everything to one thread. And then when we try to introduce parallelism, we get into trouble. Reactive programming doesn't throw that parallelism away. However, because it's got this strong consistency guarantee, the problem of how to parallelize it has not really been solved. So there is there's potential there, but it hasn't been realized yet. But you can code now and work on the engine later, because I think that the potential to optimize it is huge. If you're prepared to take a small performance hit now, because it's not as fast as Observer. So basically, it's still pretty new technology, and it hasn't received a lot of investment. So that's why the potential is nowhere near realized. But the model itself is actually really well defined now. It's been thrashed out enough that people are pretty happy with it. So performance, I'll just talk about them independently. So it's consistent. Observer can be, in some situations, exponentially bad, and that's because you get, when you are combining a whole lot of things together, you get two inputs this way, and then it will propagate twice. So it's not a big thing, but with reactive programming, it's a little bit more consistent generally. So yeah, I think there are a lot of performance improvements possible. Now parallelism, just what I was saying before, consistency guarantee is a problem. It currently is not that great for parallelism because this problem hasn't really been solved, but the approach I've taken when I've needed to use it in parallel is to add a primitive that relaxes the consistency guarantee, and that seems to work quite well. So it can be done, but it's not a brilliant thing at the moment. But I believe there is quite a potential with it. But anyway, I got asked about this one, testability and refactorability. It's quite excellent because all your dependencies are explicit, just like all forms of functional programming. So it's got all those advantages. And this is quite a big one. The compiler is very good when you program in this style at detecting anything you do wrong. So you will generally get a compile error if you refactor something. So it's very safe. You can just happily move code around and it'll compile when you get it right. Okay, debuggability. I got asked about this one. You can put traces on things, but execution order is generally all over the place, so it can be a little confusing, but if you're just looking at one value, it's not a big deal. It seems to work pretty well. Standard debugger is a little annoying because it goes back and forth between the app and the reactive library, because that's what the control flow does. A specialized debugger is something that might be really brilliant, but such a thing doesn't exist at the moment. Generally speaking, bugs are rare because of the style of programming. It means that you're just dealing with the logic, so they're certainly not eliminated, but a lot of the really silly bugs just don't happen. So, and here's another anecdote. Our predominant source of bugs was not understanding the problem we were trying to solve. Right, now here's an anecdote from a couple of weeks ago when I was working on a game. Sadly, I can't show you the games because I can't make my computer work on this. But if you want to crowd around later, I could show you the games briefly. But I'll tell you what the games are. Okay, so I've got 3 games. One of them is a times tables game for children, and it's a commercial game, and it's about to get on the iOS App Store. So that's the most advanced program I've done in Sodium so far. The second one is a free cell game, which is just one of the examples I put in the Sodium library. So that's quite nice to look at because it's reasonably complicated, but simple enough that you can use it to learn how it works. And the third game is the one I'm going to show you the code for, and it's the simplest game I could think of that was vaguely playable. Yeah.
The one that's on the iOS store, which language you used?
Oh, that was in Haskell. Yeah. Yep. So, right, so here's my anecdote. I was in a hurry. I just thought, I've done mouse drag a few times. I'm going to just make a real general version of it, and then I'll know that I could just use it for anything. So I just kind of threw it together, and I thought, oh yeah, that'll work. And then I ran the program, and it worked. So that's the kind of thing you get with, because you're just dealing with the logic. A lot of the stuff you don't have to care about a lot of stuff to do with event order and all those kinds of little details and edge cases and invalid states and so on. So it can be possible just to bang the code out, and when it compiles it works. So it's not not perfect in that regard, but it can be pretty good. Okay, so this is what a reactive system generally looks like. You have inputs going in and you have outputs going out, and this tends to be just pure logic. So if you've got a video game, it would be touch events or mouse events, and outputs would be spaceships and sounds and whatever else. And your I/O is typically done outside the system, so you would generally have something going out here into the I/O and then back in saying, yeah, I've finished, or here's the result, or whatever. Right, now I'm going to tell you what a reactive programming library looks like when you use it. There are 2 data types and 8 primitives. So these 2 data types, in some reactive systems there is only one, and it's called signal. But this is the most common, and this is what Sodium's got. Okay, so this here is Haskell syntax, and this is pseudo Java syntax. So just read whichever one you're most comfortable with. So an event represents a stream of events, not an individual event occurrence, which is quite important. And you're generally working with the entire stream, not just the individual occurrences. So you don't get a value, do something with it, and then send it over here, like you would generally do when using the observer pattern. So an event has a payload as well. So if it was a mouse event, it would have the mouse position and what button was pressed and all that kind of information attached to it. Okay, so all this business with adding and removing listeners that you have in the observer pattern, it doesn't appear in your code anywhere. It's factored out, and same with notifying. It's just not really in there. Okay, now this is more functional reactive programming history than anything else. There are 2 main views on time. In the classic FRP, time was behaviors are seen as continuously varying, and so that they're functions of time, or in some way continuously varying. And events have time stamped on them, so time was built into those systems. And with Sodium and a few other systems, we've just taken time out altogether, and just so there's an order, but there's no time. If you wanted time, you just add it as a separate behavior. And the changes are discrete in Sodium. Some systems allow for a function of time, but that's the way I've done it. Okay, now a behavior is a time-varying value. It's also called a signal, but like I alluded to before. So we might have a spaceship position or a vehicle speed or anything that varies over time. The clock time is another example. So you can think of behaviors like events that remember their last value, but again, I just wanted to emphasize there's this whole question of whether they're continuous or discrete. In Sodium, I've generally chosen convenience over purism. So in Sodium they're discrete, but you can pretend they're continuous if you like, using various tricks. Okay, so now I'm going to tell you about the first 4, which pertain to events. Okay, so the first one is never, and that's an event that never fires. That's useful as a placeholder or whenever you want something that doesn't fire for whatever reason. That comes up a lot. So map is where you modify the contained value. So if you had the mouse position, if you had a mouse event, you might want to extract the mouse position out of it. So that would be a map. So that turns an event of mouse event into an event of mouse position, for example. So filter is just the general concept of not always allowing an event through. So sometimes you don't propagate. So you would have an optional value, and when it's some, then it goes through, and when it's none, then it doesn't. And merge is where you've got two event streams and you merge them into one, and they have to be the same type because they're going into one of the same type. Right. Now, events can be simultaneous, so there's a big question. Yep.
One of the things you mentioned earlier was that you don't have time in the system, so events are ordered by the order that they occur.
Yeah.
How do you merge them? How do you have consistent merges?
Yeah, that's a good question. I haven't really. Yep. Oh, yeah, certainly. This is pretty much, yeah, because we don't have timestamps on them. How do we decide what to do? How to keep them consistent? So that's about all right.
For a merge specifically.
Yeah, for a merge. Yeah. So that's what I'm talking about here. So if you split an event into two, then they are simultaneous, because in most of these systems, well, I think pretty much all of them, there's the concept of a transaction. So you can think of events being in the same transaction as being simultaneous, because generally they work that way. So then that raises the question of what do you do when you merge two events that are simultaneous? Well, that is actually quite a difficult question. And Conal Elliott, who's one of the people that invented this idea, has written multiple papers on it. What we do in Sodium is, because it's the common cases where you don't, you're not expecting them to be simultaneous, we just make it so that it fires twice in the same transaction if they are simultaneous, which can be okay, and often is okay. There's also an operation called coalesce, where if they fire in the same transaction, then we combine them using some combining function, and then so that's how you get around that problem. But it does retain the order. So, but the order may or may not be meaningful. Sometimes it can be. So
just to clarify,
yeah.
you took a string
Yeah.
and applied two map operations, two filter operations, such that the string is completely fast.
Yeah.
That would not be an independent operation.
That's right. Yeah, and that does it does work out that way quite a lot of the time. Yeah. But not always. So it does come up. Yeah, and so I don't think there's a really simple answer to the question anyway. Right, next one's hold and snapshot. These pertain to behaviors. So hold is called stepper in some systems. It also has other names, but what this does is it has an initial value, and then when an event comes along, it changes the value of the behavior. So, for example, yeah, I can't think of an example. Okay, so snapshot is sort of the dual of it, because what it does is it takes an event and it samples the value of a behavior. So if you combine a snapshot and a hold together, then you can make that turns into an accumulator. So the hold keeps the state, and the snapshot reads the old state and then applies some function to it, because here we've got a tuple, but it's commonly used with a function that decides what to do to combine these two values, and quite often you will throw one of them away or whatever. So you can do whatever you like with that. Okay, so next one is, I'll give an example later, so hopefully that'll make sense. Next one is lift. Lift is a really important concept. It's a functional programming concept. So the idea is that we've got a function like plus that just adds two numbers together, and then we've got a count of transmit packets and a count of receive packets, and then we just add them together, and that gives us the count of total packets, for example. So if this one increases, then that one gets updated. If this one changes, then that one gets updated. If they both change at the same time, this is common to all reactive systems that I know of, it will just update that once instead of twice, and that's called a glitch if you don't do that. So that makes the whole thing work much more cleanly. Okay, so what it actually does is it takes a function that works on values, and it gives you a function that works on, actually that's my next slide. These are the, I'll get to that. So these are the type signatures anyway. Hopefully that's useful. So you give it a function from A to B to C, and a behavior of A and a behavior of B, and it gives you a value of C. But it can be better to think of it as lift as something that takes a function on values, and like I said up here, it can be any arity, and it gives you a function that operates on behaviors. So you're lifting the function into the world of behaviors. Functional programmers will know that idea. Okay, so the last one is quite an important one. It's switch. So it allows the reactive network to change dynamically, because everything I've described up until now is fixed. It has state, but the total amount of state can't change, basically. So holds are the places where state is kept. So it's like we're using reactive logic to modify reactive logic. Okay, so I'm going to give you a really good example of switch here. This is the type signature. Behavior of a behavior of A gets turned into a behavior of A. And here's the Java-like version of it. So it's a behavior of A turning into a behavior of A. So we're sort of flattening it. So any functional programmers out there know what this is called in functional programming. That's the one. Okay, so right, here's my example. Now, I'm going to show you this code, and then I'll show you a diagram, and then I'll show you the code again. So that should make it really clear. The idea is that we've got three video streams. So I've modeled a video stream as a behavior of image. Now, that means that a video stream is an image that changes over time. Simple enough concept. So we've got three of them. First one is fuzz, which is just the fuzz that you get when you're not tuned to any channel. This one's channel 1, and that one's channel 2. So we also have a remote control, and it's got two buttons on it, and I use the convention of putting E at the beginning of events, so that indicates an event. So what we're doing here, and this is a little bit of Haskell syntax, so apologies for people who don't follow this, but I'll try to explain it as best as I can. What this is doing is the button has no payload, it's just got an empty value because the button doesn't have any information associated with it. So what we are doing here is we're throwing that empty value away, and we're replacing it with that value, which is a behavior of image. So the type of this is event of behavior of image, because we're going from an event of null value or unit value to an event of a behavior of image. Does that make sense? Okay, and then this one here, we hold it. And when you haven't pushed the button yet, and this is a good example of this business of the default value, when you haven't pushed any button yet, it'll start on the fuzz channel. And then we get those two event streams and merge them together, and then we just feed that in. And the type of this one is behavior of image. So if you think of a video stream as being an image that changes over time, then you can think of a TV where you can change the channels as something with a video stream that changes over time. Does that make sense? So that's why it's behavior of A, behavior of image. And with switch, we flatten that down into behavior of image, and then that is what goes on the screen. So I'll give you a diagram of that. Okay, now that there is a news program, and that one's a nature program. So here's our remote control. So when we push this button, it takes that value, it throws this value away because there is no value, just takes that value, feeds it into the merge, and it holds it. And here's our default of the fuzz. So we push the button, and I'll show you what that looks like. That's like that. There we are. So this shows the event firing stage of processing. So events change state, and events don't exist between firing, so they don't retain any state afterwards. So this is what's happening instantaneously. Instantaneously we get this value, feed it in here, merge these two streams together, feed it in here, and then when we switch it, it goes from being that structure to that structure, which is just a video stream. And then that's what it looks like afterwards when we've switched. So that's pretty much the same, except that that's now changed. And there's the code again in case you want to have a look. Yeah. Okay. There is an event variant of switch. So what it does is it has a behavior of an event of A, and it gives you an event of A. So what it represents is an event that's changing over time. So remember, an event is an event stream. So it's an event stream that changes over time. So what it allows you to switch between inputs to some piece of logic using the value in a behavior, and the behavior is the thing that switches between them. Okay, so here I'm just going to talk about state for a bit. We don't have mutable variables like you do in normal programming, and the reason is because everything's done under a transaction, so we don't want anything that is not done under a transaction like in standard mutable variables, so that's why they're banned. Right, now here's a little bit about the interaction between events and behaviors. So you can think of events as being the things that cause changes to happen, and behaviors as being the things that hold the state. So separately, if you just have one or the other, then you can't have any state changes. So you need the events to act on the behaviors. Another point which I alluded to before is that all state changes caused by a single event occurrence are atomic. So it's just like a database, there's no notion of the order that things are updated in. So that's what, essentially the idea is that you don't have to care about that. You just have an event that happens, and then it gives rise to a whole lot of state changes that are seen as being simultaneous. This illusion is not perfect because remember I was talking about events being simultaneous. They do actually have an order, but there are a number of reasons why. Yeah, so it just gives rise to this idea that you just don't have to care about a whole lot of different stuff. It takes a lot of the work away from you. Okay, now I'm going to give you an example. I can show you, if we create around my computer, this running, but what happens is if you click somewhere that's not on a crate, it'll create a new crate, and then the crate will fall down, like that. And if you click on a crate, then it will smash, basically it just disappears, and then the crate above it can fall down. So we've got creating a crate, which makes a sound, which is a pop sound, and then we've got destroying a crate, which is when you click on the crate, and that makes the crate make a smashing sound. And then when the crates exist, they have some physics, and they also have some collision detection, so they can sit on top of each other, like that. So I'm going to show you all of the code for this game. So this is going to be a bit of an effort, but it was surprisingly successful last time I did this talk, so I think we'll see how we go. Okay, so what I'm basically showing you here, now this is Haskell syntax, so it will be a little bit unfamiliar to some of you. Basically, with Haskell syntax, with normal programming languages, you have, when you call a function, you have parentheses, and then the values, the arguments, separated by commas. Well, basically in Haskell you just don't have that. You just have spaces instead. So that's the major difference. Okay, so now this is a type signature of a function, and the main point of it is that the last element here is the output value. So these are the input values, and that's the output value. So I'm just showing what the input and the output are, and I've put them into data structures. So we have event of mouse event. Now this code is, all the code you've seen before was pseudocode. This is real code. So this code actually runs. And if you want to see this code, it's at reactiveprogramming.org, and if you fire up your compiler, you can just compile it and run it. Okay, so right, inputs. Okay, we've got an event of mouse event. Now P is just means platform, so I just use that to make it cross-platform. And then we've got time, which is a behavior of double. So that's the number of seconds since the game started. The output values, we've got a behavior of sprite, so that represents everything on the screen. And then we have sound effects, which is an event of sound. So when the crate is created or destroyed, you get a sound. Now these are the resources that they're just constant values. You see that it doesn't say behavior or event on these. So that's the picture for a crate and the picture for grass, because there's a band of grass at the bottom. And then those are the two sounds.
So what's the P?
The yeah, that represents platform. So that's just so I could make it cross-platform. So I can have a different implementation for each. Oh yeah, but it's because it's a bit long. I'm going to cover it on the next slide. Yeah, that's okay. Now another thing about this is this program has a value loop in it. Value loops are something that you get in functional programs. It's also something that you have in reactive programming, and a lot of people are unfamiliar with them, but essentially they just are forward references. That's all they are. So what this, I can't define everything before I show it because it's all in a loop. So you'll have to just take some things as read until I get to them. Okay, so this is where you create a new crate. So what we do is we get our mouse event. We've got two input values here. We've got one called rects. That's from the loop, and that tells us that's a list. It's a behavior of a list of rectangles that describe the positions of all the crates. And eMouse is our mouse event. So what this does is a snapshot with, we pass it a lambda here that just gets the values and then outputs something. So we're using, whenever there's a mouse event, we're snapshotting the state of what all the crates are, and then we're doing some logic on it and we're outputting something. And then we use filter, so we only where it says just do we actually pass the value through, otherwise we discard that event occurrence. Does that make sense? So this is the lambda here. That there is the symbol for a lambda or a closure in Haskell. So we just take the mouse event and the rectangles, which is the list. So then if it's a mouse down event, then we grab the point. This here is Haskell meaning if. So we get the point, the position of the mouse, and then if not any other point inside recs, which means if none of them, if it's not inside any of the rectangles, then we create a new one. If it is inside of the rectangles, then we destroy that crate. So that's another piece of logic. So then we just go just point. So that gives you an event of point. So point is just a tuple of floats, basically. It's just a position on the screen. Okay, so that there represents the positions of newly created crates as they happen. Right. Now, Haskell doesn't have the concept of pointer comparison. You only have values. So if you want to identify something, you need to have an identifying number associated with it. So what this does, this function here, identify, so this is a function call that's saying identify this and give me it tupled up with an ID. So it's taking an event of point and then it's tupling it up with a unique identifier for each one. Yep.
So the arrow in place of the module?
Yeah, that's right.
That's
No, this is called reactive, this monad, and it is, you can imagine it's not there because it's needed for the sort of implementation of the system, but you don't have to you don't have to think of it logically as a monad, if you like. Essentially, if you get a function full of sodium code, you can rearrange the lines in a random order and it will work exactly the same. So there's no flow of control. It's all. So the monad's there for implementation reasons, really, not for anything other reason. Okay. Yeah, actually, Conor Elliott, who's probably the main inventor of reactive programming, he did a system called Reactive, and he was trying to get rid of the monad, basically, and he never quite achieved it. So I think it is quite difficult. So I've just cut all the corners I can, and I wanted something that was practical and worked and was solid, and you could build commercial applications with. That was my design philosophy behind Sodium. Okay, so here's how identify is defined. Now this is using something called count, which I haven't told you about. Essentially it's just, I have actually put this into Sodium, but I'm considering taking it out. But essentially what it does is it counts the number of event occurrences here. So this is a behavior of int. And so every time there's an event, this count goes up by 1. And then what we're doing here is every time there's an event, we take the identity and we snapshot it, and then we just tuple it up with the value. So it's as simple as that. So when an event comes in, two things happen. One thing is this count goes up by 1, and the next thing is we capture that count and then we just attach it to the value of the event. Now you might be wondering which one happens first, and this is an implementation detail of Sodium. Different reactive systems take a different position on this question, and the question is when is the state updated in the behavior? Now what Sodium does is it delays all state updates. So whenever you use a snapshot, you're reading the old state. So the initial state of count is 0, so the first value will be 0. That's returned here. Okay, now that's the line from the previous slide where we had event into point. Now all we're doing here, now this one here is a primitive that I did not tell you about, and this is another byproduct of this reactive monad. So it's just an implementation detail, really. But what we're doing here is we're saying every time there's a new crate created, we use this function called crate, which I will get to soon, and that handles all the logic for the crate. And these are its inputs. So if this was not Haskell, it would be parentheses and commas. So the first one is the unique identifier of the crate. So this is a similar structure to what you saw before. We've got a lambda here inside a map. Well, actually we had a snapshot before, but it's basically the same idea more or less. Okay, so the crate takes this unique identifier, it takes the initial position, which is a constant. So these are constant values now. They're not behaviors, because we're now inside. We're operating on what the map does is it operates at the value level. So we're actually operating at the values here, not an event. So it doesn't pass an event of these two, it gives you the actual value. And then crates is from our program loop, and that is like rects that we had on the previous slide, which was the positions, but it also has the IDs with it. That's the only difference. Otherwise it's the same concept. And then we have time, which is our behavior of double for the animation. Okay, so what this type is an event that contains a behavior. And the behavior is returned by this function crate. So it gives you a behavior describing where the crate is. So the job of this is to take the other crates and time and to tell you where that crate is. So it doesn't handle mouse events, but you could make it more complex and make it handle mouse events if you wanted to, but we don't handle mouse events inside there. So that's it. And all this does is it turns it into, it takes that here, which is the unique identifier of this crate, and the changing position of the crate. And it turns it into a map insert operation This is Haskell standard library stuff, which is just inserting into a dictionary or map. So that's all that is. And then so that becomes an event of some function that modifies the map of existing crates. So then, what's this? Oh, okay, this is the bit where we actually use this. Our crate map is a behavior that contains a map from unique identifiers to the changing positions of the crate. Does that make sense? So then Hume is a combination of hold and snapshot. It takes functions that perform changes on the value and then applies those changes. It's just accumulating changes to a value, and the value is it starts off as an empty map. So those are our crates that we start off with. So this is a bit like hold. This is the same basic idea as destroying the crate. So we get a mouse event, we get the existing crates. This time it's crates rather than rects. So crates is just a tuple of int and rectangle, or int and behavior rectangle. Oh no, it's int and rectangle. So it's the ID and the position of each crate. Okay, so mouse down event, and then what we do is we iterate over the crates, and then whenever there's one that's inside the rectangle, we make one of these changes to accumulate, which is a map delete of the event. So we're just saying, just delete the event from the map. So that's pretty straightforward. And here's the same line I had on the last slide, which is accumulate all the create and destroy events and give us a state of what our crates are. Okay, now this is probably the most important thing to understand in the whole thing. This is where we use a switch to flatten the behavior of behavior, because I don't know if you remember, we had an event with a behavior inside it, and what we want to do is we want to flatten that so that we get a list of what all the current crates are that we can actually manipulate, because when you can't, yeah. Okay, so first part here, we have a behavior of map of int behavior rect. So what that means is that inside this behavior we have a map from the ID to the changing position, because a behavior is a changing value, the changing position of the crate. Here all we're doing here is we're turning that map into a list. So this has nothing to do with sodium, it's just map to list. So we've just taken that map from int to whatever and turned it into, oh wait a minute.
Brought the behavior out as well.
That type's wrong, I think. Okay, anyway, look at the next line. Should make sense. Yeah, I think that behavior is wrong. I mean, I think that type is wrong. Oh no, sorry, the type is not wrong. Okay, I've got it now. So basically, we've taken this int and we've actually put it inside the behavior, and we do that using a map. So I called it map, but in Haskell it's called fmap, but it doesn't matter, it's a map. So what we do is we get the ID and the behavior, which is that and that value, and then we just sort of lift this one, which is a constant, and we put it inside the behavior. So that type signature is right. So it's doing a little bit more jiggery-pokery than just turning it into a list. It's also taking that value and sticking it inside the behavior. So now we have a behavior. Oh, okay. Yeah. So what this does is it uses some Haskell applicative magic, which is essentially just based on lift. There is no more magic than that. So once lift is defined, you can do this, and what it does is you have a list of behaviors, and you're turning it into a behavior of a list of the same thing. Right? So when you've got a whole pile of behaviors, you can turn it into one behavior that contains a list of all those different elements. So that's what we're doing there. And then it's really easy, just go switch, because we've got our type behavior of something, then we just go and we switch it and we turn it into a behavior of something. Okay. So then that there is crates, which you might recognize from code. code before. That was when we did a destroy, when we wanted a list of all the crates, identities and positions. And then for the for when we created the crate, we didn't care what the identities were, so we used this one. That's all that is. So we're just taking that value and throwing it away. There. Okay, nearly there. So sprites and sounds, this is very simple. You get create event that we used to change the state before, and now we reuse it. We just get our resource and we turn it into an event of sound. And then we do the same with the destroy event. We just get our destroy sound and we put that into the payload of the event. And then we merge the two together. And here's another, this is a case of what I was talking about before with the merging events. In this situation, we know just from our own logic that creates and destroys can't happen in the same transaction. And so when we merge them, we know they're not going to be simultaneous. So that sort of tends to be the way it turns out a lot of the time, but not always. Okay.
Sorry.
Yeah.
This is what you were talking about, but this doesn't work in a distributed environment. You need to have a global view of the system that you take a transaction, do some updates.
Yeah.
If you're in a distributed environment, you'd have no way to distinguish which one happened first.
That's right, yeah. So this stuff really doesn't work in a distributed environment. Could possibly be made to one day, but it doesn't at the moment. Okay, so here, this one here is the same basic idea, only we're dealing with behaviors. So what we're doing is we're getting this function draw crate that takes the rectangle. A drawable is a function that takes a position and then gives you a sprite, and the sprite is something that can be drawn on the screen. So we just are running that draw function that just turns it into a sprite. So we take the positions, turn them into sprites, prepend the grass onto the beginning because we want that at the bottom. Then we concatenate all the sprites together into one sprite, and away we go. And all this does is returns them out the bottom of the function. So that's very simple. Okay, and this is the logic of the crate itself. So remember the arguments that we had before. Here are the types of them. So we take, it's got 4 input arguments and 1 output argument. The inputs are, or 1 output value. So the inputs are the unique identifier, the initial position. These 2 are constants, these 2 are behaviors. This one is the position of all crates because we need to do collision detection. So we've looped that round our whole program and fed it into each one. So each crate has a view of where all the other crates are. And that's just our time behavior. Okay, so at the beginning of the function we want to get our list of crates and turn it into a list of obstacles, and that involves deleting myself because our job is to work out where we are. Our job is not to work out, we don't care about where we were before or whatever. We only care about the other crates, not ourselves. And then we just add the grass as well as another obstacle so that we can't fall through that. All this does is gets the time and turns it into a fragment of delta time for the use in our physics stuff. And this is the code to do it, and it's not really all that important, so I won't spend any time on it. Yeah. That is a... There. Yeah, so it's the unique identifier, and that's a constant throughout the whole thing. It will never change because it's at the constant level, if that makes sense. Yep. Okay, and this is the last bit. I've taken all the physics stuff out because this is not a talk about physics, plus it's really rubbish code, so I don't want you to see it. But you can actually go to reactiveprogramming.org and there's a link to that at the top. So, so if you want to look at the code and run it and so on, it's all there. Right, so what this is we are getting our fragment of delta time, and we have what this here is we've got 3 different behaviors that we want to snapshot, and we use lift to turn them into one behavior because snapshot only works with one behavior. Hopefully that makes sense. So this function here is just the double tuple function. So it takes 3 things and it gives you one thing, which is a tuple of those 3 things. So that's one way we can use lift. And then this is all just integrated, but one point is point here is I've got a boolean here for whether it's sitting or whether it's falling, so that's part of the state, and so the initial position is false, and position is the integral of velocity. So integral, I think, doesn't matter too much anyway. It's not a great important detail.
What is the REC at the top there?
Okay, this is a Haskellism, and it just means that we can have forward references. So it just enables a loop to happen within a monad. So when I say loop, I'm talking about a value loop. So in other languages, so Haskell has this concept of value loops, and all it is the ability to do forward references. So your whole program can have this value that has a cyclic dependency going all the way through it, which works fine in reactive programming. It works very well indeed, actually, in reactive programming. In other languages, I have a primitive for doing that. So you just, at the bottom, you just take the value and you feed it back into the value at the top. And so
in this case, velocity and position are both used in the calculation.
They're used here and they're defined here. And EXL is used here. So the whole thing's a loop.
So in JavaScript, you'd have absolutely no issue because it allows references to,
Oh yeah.
to the scope, even if they occur after the event.
Yeah, there is a JavaScript implementation of this, and it's called Flapjacks, but I think it's pre-compiled. Okay, so that's it. I would like to show you the games, but unfortunately this isn't working. So perhaps maybe we could eat some pizza and then maybe I can get my computer working on there or something. And if not, we can just stick it up here or crowd around it or whatever. Yeah. Certainly can.
One thing you can do is far better than listen-based or observer-based systems where you mentioned that this is more suitable for concurrency.
Yeah.
If you need to take a whole world's log, why does that make it more parallel?
Well, essentially what I'm saying is it doesn't make it more parallel in practice. It doesn't make it more parallel in practice. What it does is it allows you to write your code in such a way that, in principle, it's parallel, if you see what I mean. But that's an unsolved problem. That's really the best answer.
Use create automatically parallel?
No, not that I know of. No, but it's possible that I'm wrong about that. Yeah, when you think about the problem, there are ways that you can see of doing it, because automatic parallelism is actually quite a tricky problem. So
You need to somehow segment the program to parts that didn't interact.
yeah, because that's actually relatively easy to do, because what I'm doing in here is I'm just putting a dirty great mutex around the whole thing. So that's really, like, not really solving the problem at all. So what you can do is you can just put mutexes around the individual bits of state, but you're probably better off actually, but that would deadlock, so that's not good. But it would probably work if you use STM, which is software transactional memory. It might just work straight off if you do that. So as long as there's no contention, it should be parallel, but you still have to have this concept of a transaction, so when they do collide, it's got to be in the right order. No, I don't think so.
You would find the problems, the contention until we reach
Oh,
deadlock.
So with STM, you have to actually deal with the flash. So if you retry it, or you can abandon the transaction.
yeah.
So you have to
It wouldn't
consciously respond to it.
It wouldn't be transparent to the user for that really.
No, you have to actually make the decision.
No, I think it can be done transparently to the user. Yeah, but the thing is, what we're really doing here is we're specifying it at a really abstract level. So you could say that instead of throwing the parallelism out the window, like you do with Observer, what you're doing is you're kind of keeping it around just in case you can actually exploit it.
Sorry,
Yeah.
Observer doesn't throw away parallelism, it's just that it's easier if you do.
Yeah,
You
yeah.
don't have to worry about
Well, that's true.
how
Yeah.
those hits.
Oh,
Whereas this,
that is absolutely true. Yeah.
as a primitive sense, then no, we can't have parents.
Yeah, yeah, that's right. So it is worse in that respect. Yeah, but
But in practice, it makes
yeah.
it more friendly. It's like,
Yeah, but I do have a solution to that, which is very simple and works and is not all that spectacular, really. But essentially, what you do is you divide the code into what I call partitions, and they're just separate reactive transaction states. So then they run independently, and then if you want to communicate between them, then it's an asynchronous connection, a bit like an actor, you know. So, and that's just a primitive. So then but there's a type parameter on the events and behaviors, which means that you can't mix them up by accident, right? So it's like you're running several threads of reactive system, but they communicate through asynchronous channels, and that's easy to do. So that solution does exist, but more sophisticated solutions are potentially possible. Yeah.
Just to stay on this topic, have you heard of something called transactional lock elision?
Transactional lock?
Lock elision.
No.
So it's a technique that's emerging on new hardware. I think that some Intel chips have it. And the idea is that the chip itself is able to determine when the code is taken a lock and when the code is leaving a lock.
Yeah.
And it will actually attempt to elide that acquisition of the lock and continue in parallel and then detect potential conflicts between different threads.
Oh, that's pretty cool.
At the hardware level. It uses kind of caching stuff. But it's not science fiction, but it's not common yet.
Right.
But that kind of thing, it makes the idea of having just one mutex taking a whole lot of state a lot more plausible.
Yeah, yeah.
And without getting into the kind of complexities of having these buckets of state that are kind of somewhat independent.
Yeah, yeah. Well, the problem is, the problem is with using the observer pattern and just trying to solve the problem today using that methodology is it just creates a lot of problems, which just end up being a maintenance problem. What this does is it gets rid of the maintenance problem, but doesn't really solve the problem as such, if you see what I mean. But yep. Carry on.
Oh, yeah, that's more than cycle. I was just going to ask, I was going to play around with that reactive banana library, and I was wondering if you think there are any pros or cons of using your library or physical reactive banana.
I did have someone tell me that my one was easier, but that's all I can really say. I think that reactive banana has time in it, so it's slightly different style. But if you want to give them both a try and tell people what you think or whatever, that'd be good. So I don't really know. Oh, incidentally, I called it sodium because I didn't have an internet connection at the time, and it was the most reactive thing I could think of. But it turns out that bananas are high in potassium, and potassium is more reactive than sodium. So I don't know what that means, but yeah. Anyway, yeah.
one thing you mentioned earlier on was that reactive programming is quite good for existing products because you can introduce it yourself, you don't have to switch.
Yeah.
I'm not sure if I see how that would work because it seems like you need to write your program in a particular style so that you're operating over sort of continuous streams rather than over individual links.
Well,
so how would you integrate?
How that would work is you would just get one little piece that's self-contained. Let's say just one source and one listener, one source and one observer, and you would just use reactive programming just there and replace that, and then
to lift in the traditional event source into it.
Oh yeah, because on the outside it's just observer, right? So this when you actually use this code, because there has to be imperative code somewhere in your program, otherwise it won't do anything, right? So what this does is what you do is you just take your event and then you say, call me back when it's updated. So it's as simple as that. It's just a straight observer. So all you do is you just put it in one place using reactive programming instead, and then wherever that is used, you just replace it, and then you've got observer from then on. And then later on, you might come along and you just extend that a little bit. You know.
So you want to do it the other way around, so you want to use an event to wrap it and flip it?
You can, yes. What you would do is that's on the other side. So you create, when you create an event at the imperative level, it gives you in the C++ version it's a send method where you can just poke a value in, and on the in the Haskell version it's a function. You just pass the value in, and it will, or it's actually an I/O action. You just pass the value in inside a transaction, and then it goes in. So yeah. So you can actually just listen, have a bit of observer-based logic, and then at the end just poke the new value back into reactive world. So it actually works quite well for refactoring from an observer program. Yeah.
I know the grand central dispatch format uses the type of
Oh.
How about you are in a position to compare the
I don't know anything about it.
Okay.
I haven't heard of it. Yeah. What do you know about it?
It's intended to be a polling loop that all the things that the polling loops will share, so they can all composed together.
Is that
I
anything?
don't know what can be passed through it.
Oh, okay. It sort of sounds actor-ish, sort of, possibly.
The big advantage that they sell it for is on mobile devices, where you don't want to wake up the device for every single program that wants to do polling. So you wake it up once, do all of your polls, and then back to sleep.
Oh, okay. Yeah.
I think there's other advantages as well. That's what they
Yeah. It sort of sounds like it's solving a slightly different problem, but I'm sure it's related. Yeah, because events are, everywhere in programs. Yeah.
I was going to suggest we have pizza
Yep.
and we carry on discussing.